we were discussing about the loader design option. Among that, we have seen the linkage editor, which will going to do the linking as well as reallocation, and creates or writes it into a separate file, which we call it as an executable file. Like in our UX and like in our Unix, we're going to create a, means after compilation and all the linking is done, we're going to create a.out file, which need to be loaded onto the memory and reallocated by a reallocatable loader. So means the linking and the reallocation would have been done using relative addresses. This is what we call it as linkage editors. The second design option which we discussed yesterday is dynamic linking. This dynamic linking will link the required libraries, required symbols during the execution time, not before the execution time. But the linkage editor does this during the compiler or assembly time. Actually, we cannot call it as compile time. Compile time will give us the assembly language code, which will be fed to the assembler. Assembler gives us the object code, and then it is given to the linker so as to create an executable type or the binary file. But the dynamic, dynamic loaders or dynamic linking will link the required subroutine or the required symbols during the execution, particularly for the libraries. Usually, the libraries will be a huge object code files containing the description of lot of library routines, and if we attach it with every program, the size of the executable will be obviously bigger. So majority of the time it so happens that the operating system may not have enough memory to allocate to your program. So as to avoid that, we're going to go for a dynamic link. Fine. And the required object code or required library routines will be linked during the time of execution. And this also allows us multiple programs in the memory to use the single copy of the libraries. This we call it as a dynamic link libraries. And majority of the compilers will go for DLLs or dynamic link library only, rather than going for other sort of thing. Fine. Yeah. Yesterday we discussed the concepts related to this. We have seen one example. If a routine which checks for the errors is there, and usually if there is no errors, this function will not be called. There is no point in adding or providing the memory or loading or linking this particular thing or error handler for every program. So for that reason, this will be kept separately and only linked to your object code if this particular error handler is called. If the error handler is never called, if an error never appears, this particular error handler will not require to be linked with your object code. So the point why we do this is there will be many subroutines, and each subroutine is many library functions. Each of these library functions may not be used, and it is going to be only allocated or linked to your object code if at all it is called. If it is never called, we'll never allocate the memory. As simple as that. So in the previous class, I stopped here stating a example. We shall see each diagram and we shall understand how this one will do. And usually in the exam, this concept, if it is asked about the dynamic linker, then this particular example suits well so as to explain the concepts. And the slides also have prepared in a similar fashion so that you can use it in the same way while writing in the examination. Yeah. See the figure A. There is A, B, C, D, E set of diagrams. We shall start from here. User program is executing, that is means this vertical slabs here represents the memory. Okay, and the user program is running, and now the user program wants to execute a function error handler. The name of the function is error handler. What it does, we are not bothered about it. Fine. For example, here we have taken the name as error handler. When the user program want to execute this particular code or this particular library routine, it will check in the memory allocated for it. Obviously, it will not get this particular routine because it is not been linked. It is not part of the functions which the user has written. It is a library function. And this library function is not attached to your user program because it will be attached if it is a static linking, as with the linkage. But now it is a dynamic linking. This error handler is not attached to your source program. So your user program will just transfer the call to the load and call, a routine called load and call. What this load and call does is, it is going to search in the dynamic loading stuff, means the shared copy of your library routines. That now I am telling you the shared copy of library routines. We can extend this concept a bit ahead. Let's see here. We will search in the memory where all the libraries are stored. If it is got, obviously, that will be linked with your user program, and user program can just call that particular thing just like other subroutine of your own program or your own user-defined function. But my question now is, if this particular error handler routine is not there in the memory itself, then what has to be done? Then again, your operating system concepts comes into picture. Then it will going to be a page fault. And again, the demand paging concept will happen. The required page will be brought from your, whatever you call it as, secondary storage device. And a block will be allocated for that particular thing. And then that will be loaded onto your memory. From your memory, load and call error handler, so load and call routine will going to link that to the user. Obviously, the delay will be more. Apart from that, if it is in the memory, same sort of thing happens with the cache and memory and secondary storage or virtual paging, whatever it is. So same set of steps will happen. Means to say, if the user program requests a subroutine and the subroutine is not part of your user program, then it should be brought from dynamic linking. That dynamic linking searches in the library routines present in the memory. If it is present, it is going to be taken and linked. Simple concept. If it is not, then demand paging will happen and it will be brought from the, whatever you call it as, secondary storage device. Got the idea? So it's not the disjoint things what we are studying. So the system software is much and much work with together with the operating system concepts. Fine. Okay. Now see the B diagram. In the B diagram, what has happened? We brought the error handler routine from the library, either from the memory or from the secondary storage device or either of the way. Then that particular error handler, only that routine, is linked or attached with your user program. And now it is going to be executed just like another user-defined function in your program. And it will continue execution. After some time, it has to complete the execution. Correct? No? Once it completes the execution, so that step of connecting it and bringing and attaching it with the user program is demonstrated in B as well as C. You can see the D. And once the error handler completes, your user program is not, of course your user program requested for error handler, but it was not invoked by your user program, but it was invoked by a load and call routine. Correct? It is invoked by load and call routine. Means the parent or the caller of the error handler routine is not user program, but it is your load and call routine. So the control obviously is returned back to your dynamic load and call routine. The load and call routine, then in turn, you can see in the D diagram, the load and call routine, then in turn will return the control back to the user program. It means it has become transitive. A called B, that is user program called load and call linker. B called C, that is your error handler. So C should obviously return to B, and then the B should return to A. But this is when your user routine didn't have the program. But if the same error handler is called again, then we don't need to do that because it's already there in memory and it is attached to your program. Next time the control directly transferred from A to C. So that's what is being demonstrated in means the diagram E. So this is a complete procedure how your dynamic loader will or dynamic linker will going to link those library routines during the time of execution. And what happens to error handler if after the first call? After the first call, it remains in the memory. The reason is we don't know. There may be a second call or there may be a set of recursive calls for the same routine. For that reason, it is going to reside in the user program only. With the same principle we use. So frequently used things will be used again. With that principle will going to be used. If suppose your user program is calling 10 to 20 user routines and the memory allocated for your user program is overfilled, means or is getting exhausted, then again least frequently used routines will be removed from the memory. The same thing applies just like a cache or any other or your operating system routines. The same control will going to happen. So least frequently used ones will be removed. So frequently used ones will be linked with the program and it will remain there. So this whatever I am talking is happening in your runtime image of the program, the static area. In the static area. Getting it? The static area means the code section. The code section contains the code and your routines are linked to your code section, right? And the stack and the heap are the dynamic sections which will go into grow and shrink according to the execution. Fine. That's what is the concept of dynamic link. So as to summarize, okay, we shall see the next set of slides. You can get the working of it. The program makes a local load and call, means the program makes a load and call request to operating system. That is 3.14a diagram. OS refers to the internal table, means whether it is present in the table, means or in the memory. Request a subroutine, if not found, loads it from the system library. Here it is just written system library. The system library may be on the memory, maybe in your secondary storage. If it is in your secondary storage, the demand paging concept is going to be applied. Yeah. The control is then passed to the operating system to the call routine. The error handler will be given to your user program and the user program just uses it just like at the user defined function. After routine completes, the control is returned to the load and call request in operating system. And then the OS returns the control to the program. The loaded subroutine remains in the memory so that if the second routine happens, then it should be taken. Fine. As simple as that. So 4 diagrams explaining the dynamic linking concept. Dynamic linking concept is link the routines only if it is called during execution. If it is not called, never link it to the source code. That's what is the program. Right? So, and this is called by the name dynamic binding. And the dynamic binding happens in all the programming languages in all possible ways. For example, you have written a C program, you have written a user-defined function, you have declared the header, let me call int function1, and it takes 2 parameters, int and a char. Fine. And you have defined the body of the function. All these things you have done. But in your main program or in any other function, you haven't made the call for function 1, then the function 1 will not be binded with the address. Binding of the name with the address means the dynamic linker will not allocate memory for your function 1 until it is called, until it is invoked. Your program may have hundreds of subroutines that will be binded with a memory or an address only if it is called. The same happens in your object orientation also. For example, you have created a class student, but you have never created an object of the student, then obviously memory will not be allocated for your student. As simple as that. Class definition will not allocate the memory. So this happens during the execution time. If the object of that particular student is created, then only the memory is allocated. This we call it as dynamic binding. And all the compilers or the assemblers, compilers all together will use practically in the production line and dynamic linking. Fine, because it saves space, it saves time, and it shares the same content with many other files. Fine. This is the concept of dynamic linking or loader design options. Two loader design options: linkage editors, links, compiles, assembles everything, and creates a file, something like our a.out. But the dynamic, it links and does everything, but the routines will not be linked. That will be linked during the time of execution. That's what we call it as dynamic link. So more or less, this completion of our module 2, loaders and linkers. We have seen the absolute loaders, we have seen the bootstrap loaders, we have seen the linking loaders, which does the function of linking, loading, and reallocation, all these things. Then we have seen the design options, means automatic library search, and then we have seen the design options of linkage editors and dynamic linkers. Okay, fine then. Then what else we have left out with? That's what there are some 3 concepts left out so as to complete this module 2. These 3 concepts are not the conceptual thing, they are the case studies, right? If it was a normal classes would have happened, then we would have expected 1 out of these 3 case studies for your internals, but things are different now. There are 3 case studies being discussed. Actually, there were case studies in our assemblers also, but obviously, we don't have it as part of your syllabus. That's why I didn't discuss. If it was there for the syllabus specification, I would have discussed those case studies of the same, means MS-DOS and Spark and CrayMPP. These 3 are the assemblers that have been case study. Why it is not included? Because in your 4th semester you have studied about your 8086, so which is your MS-DOS assembler. So fine then. Yeah, we have 3 implementation examples, and that completes this module. First one is MS-DOS linker, MS-DOS compilers and assemblers. You know that Maxim is the assembler for your MS-DOS, which you have used your 8086. Will produce the object program, and this will be called with the extension, and with MS-DOS, means particularly the DOS and Windows operating system, will use this 8.3 notation. Heard of it? Might not. 8.3 is a DOS version of naming convention. What is this 8.3? Is 8 characters. 8 characters is going to be the name of the file, and a dot followed by the 3 characters, which we usually call it as extension, and that 3 characters extension will represent the type of file. Yeah, after you have compiled and assembled the program in a DOS machine or in a MS-DOS machine, you will going to get an object code which will be having the extension .obj containing the binary image of the program. After compilation and assembly complete, right? This is our object code file. Okay, the MS-DOS linker is a linkage editor. Means to say it does linking, loading, reallocation all at the one. Yeah, the MS-DOS linker will going to produce an object code with the extension .obj. And it produces an executable. It uses a linkage editor which does the loading, means linking, as well as reallocation, and writes it into a file. The file name will going to be with the .exe. Now we need a reallocatable reallocatable loader which loads this .exe onto memory and start execution, and add the starting address with each line of your code, right? And these are the set of records what we use. With SICXC, we had very less number of records. We have a header record indicating start of the program is after the object code is produced. Header record showing the start of the program. Text record so as to store all the object code, and end record so as to mark the end of the object code. And we had modification records so as to specify the operands which has to be modified. But instead of that, now we have set of records like PHADR, typedef, pubdef, xdef, and lnames, segmentdef, groupdef, lidata, fixup, MOD end, right? Module end, all this set of the records. Your MS-DOS will use all these records so as to specify your object code, or means your object code file format will have all these things. Using all these things, the executable will be created, right? Object module means your .obj file will contain this set of records, and using this set of records, the object code will going to be defined. Okay, yeah. So what each of these records does is supposed to be explained. THEADR specifies the name of the object, right? It's just like it's specifying the name of the object module, right? Mod end, as the end of the module, is something like your H and E, which is indicating your header record and end record. Similar to your THEADR and MOD end, we're going to specify the name of the object module and end of the object module, right? PubDef lists all the external symbols that is defined in the module. If I relate this to our SICXC, this is just like our external symbol table which we have seen in our earlier example, right? PubDef lists all the symbols that is defined in the module, whether it is in the current control section or the different control section, right? EXTDF is the external symbols referred in this module, a reverse notation. There EXTDF used to specify the symbols that is defined in this section, but here it is the external symbols are referred in this module. Okay. Next one is typedef, specify the type of all the symbols that is been used, type of the external symbols that is been used, right? Segment definition, SEGDEF defines a segment in the object module, that is like name, length of the subject, means the length of the segment, and alignment. I think in your microprocessor programming, you have in the data segment, code segment, all these things. So similar to that, this segdef will going to define which is the type of the segment, right? And group definition define how the segments are combined into groups. So when different segments are there in your program, the code belonging to the same segments are grouped together. That's what is called as group definition. Each line of code belonging to the same segment are concatenated together. That's what we mean by group definition. L names, list of all the segments and the class names used in the program. Segdef and groupdef refers to the L names. So this gives the names of all the classes that is belonging to the different segments. LE data and LI data contains the translated instructions. It is something like our text record in our SIC and SICXC example. This is actually LE data and LI data is actually the object code of your program. Okay, right. Then we have fixup used to carry out the modification of external reference. So it is something like our modification. So how this works, it uses 2 passes for doing it. It's just a case study, don't need to be very specific of this. Yeah, similar to our SIC, the pass 1 compute the starting address of each segment. Yeah, they use PSADDR, and here it is just computing the starting address. Segments with the same class but different names are concatenated. Means to say all those belonging to the same segments are grouped together. Yeah, symbol table is constructed and associated address of each segment and each external symbols will be recorded, right? If unresolved symbols, we're going to search in our libraries. Yeah. Then pass 2, extract the instruction and data from the object module and build an execution image, because it is a linkage editor which does the linkage relatively and writes it into a file, and that file we call it by the name .exe. Okay. Process LE data and LI data with fixup. LE data and LI data gives you the text record, that is actual object code, and fixup gives you the modification record. This is actually your linking, what is happening. Yeah. So the object code is taken and is given a relative address, and each one, the fixup will going to specify the modifications for the operand addresses, which will going to be done related using the relative address, and it is related, means it is written into your .exe file. Yeah. Process binary data of these records into the memory. Yeah, obviously. Reallocation within the segment is performed and external references are this. This is your reallocation process that is happening. after memory image is completed, that is your .exe file is ready, means it will be written into executable file .exe. And this entire linker of MS-DOS, we call it by the name link, right? I think you might have used with your MASM assembler, the MASM file named that MASM or something like that. And then you linked this particular thing, no? So which is actually done manually. So these are the steps that's happening with your link, right? This is one of the case study of MS-DOS linker. Two more small are there. So the next class will do that. And that's the end of our module 2 of your, what do you call, your system software. And that ends there. We go back to our compiler design concepts and continue with that. Fine. Thank you. Thank you for joining. We'll stop here, right?